All right, continuing on with our solubility. So it says the ability of a solute to dissolve often depends on how much solute is added to a mixture. So what that means here is like if you had a tablespoon of sugar to add to a cup of water, that's going to dissolve a lot easier than if you have a cup of sugar in a cup of water. All right, so the ability for that solvent to dissolve the solute has to do with how much solute you're adding. Also, temperature and stirring also can affect solubility as well. So for example, sugar dissolves in water up until a certain point. If too much sugar is added, it will no longer form a solution. This is referred to as a saturation point of the solvent. However, by mixing the solution or even heating it, you can actually increase the saturation point. So if we were in class, we would do this where basically we add sugar to water to get to that saturation point, and then we would put it on a hot plate and heat it up, and then we can dissolve a lot more. So basically, if you see in that right hand side here, you're seeing that like there's a whole bunch of sugar that's still at the bottom. It hasn't dissolved, but if we added heat to that, we could actually increase the amount that would be dissolved. Okay, so that the one word here that we're sort of referring to is that saturation point. So the saturation point. Saturation, that word, basically means that it's like full. Full up, I'm going to say. So when you're saturated, you're full. You can't add any more. And that saturation point is the point where we can't add any more sugar for it to be dissolved. So water is often referred to as the universal solvent because it is capable of dissolving most types of solute. Not all substances, however, dissolve in water. So we talk about water as being the universal solvent. It's universal because most times we're dissolving things in water, but not everything will dissolve in water, and an example of that is oil. If you've ever tried to mix oil with water, or even if you have an oily pan and you're trying to wash it, you need soap because water will not dissolve oil and it won't wash it off of your dishes. So oil and gas are both insoluble in water. This is why they're so harmful to the environment. So if you look at that water that's got oil basically sitting on it, oil is less dense than water, so it floats on top of it. And it's not a good thing because like animals, for instance, could try and land on the water, like ducks and stuff, and when they get that oil on their skin, it can actually start to make them go into shock and they'll eventually die. So oil, not good for the environment, not good for fish because obviously they're in the water, they're breathing in the oxygen from the water, and they could be coating their gills with oil. That would also kill them too. So lots of things, reasons why oil is bad for the environment. And the main reason, I guess, here, or the problem is that it is not soluble in water, so it just sits on the top. But that could be a good thing in the sense that it might be easier to get off the water when we're dealing with trying to clean up like oil spills and stuff like that, but it's still very difficult to get out of the water. Although solutions may look like pure substances, we know they are composed of more than one type of particle. We should therefore be able to separate any mixture into its individual components, and this is especially useful for the purification of water. So separating mixtures, if we have a mixture of, let's say, salt and water, what can we do? Can we separate it into salt and water? Well, we can. This is showing you an example of how we would purify water. So if we took water from a stream, it says coagulation, which is alum surrounds dirt particles in the water and causes them to become heavy. So we use different chemicals, I guess, in the water purification process. So The first step is that it's getting rid of the dirt out of the water. The second thing is sediment, so heavy particles. So all of those heavy particles will sink to the bottom, leaving the water clear on the top. We'll take the water off of the top, put it through a filtration process to remove any solids that are in the water. Then the fourth step is disinfecting it, so using some sort of chemical normally. In a lot of waterways, we use chlorine. So chlorine is added to the water to kill any sort of bacteria that might be in it. We can also use UV light to kill any bacteria. And then the last step is storing it. So purified water is stored for later use, and that would be what would be pumped into our houses, for instance. So there is processes to separate things out of water. It might take a lot of steps, and that's why sometimes it's not really economical. Like when we say we don't have a lot of fresh water in the world, well, we do have a lot of water in the world, just not fresh water, and that we would need to take the salt out of the water, and we can do that. There is a process to get rid of salt out of water, but it's an expensive process and a lot more time consuming than if we were to just purify already non-salty water, basically. So that's what we do for the most part. Water can also be purified through a process known as distillation. During this process, water is boiled and the steam is collected. As the steam cools, it condenses to form pure water. Anything that was dissolved in the water, such as salts, minerals, and harmful bacteria, is left behind. So this is in chemistry, normally the way that we would separate water from the other things in it. So you just heat it up, the water boils, all of the steam that is basically gets collected in a different sort of container, and that steam eventually will cool down, and what's left would be just pure water. And if you go to the grocery store or pharmacy or something and you see those jugs of water that say distilled water, that would be how they've created distilled water. So they've heated it up and then got pure water out of it. Distilled water is not a good thing to drink because it doesn't have any minerals in it, and we need minerals in our water because that's important for us. But also if we drink water that doesn't have minerals, it can actually leach minerals out of our body. So the best water to drink is water that has like a higher mineral content, good for our health. All right, so that is that first section of topic 3. I guess I'll continue on to this last part. So this is talking about acids and bases. And maybe you guys have talked about these in the past. In grade 9, I believe, you should have talked a little bit about acids and bases. But we've got acids and bases, and basically they have quite a bit of different things that make up what an acid and a base is. So an acid normally tastes sour. So if we think about foods that we eat that might taste sour, those would be acidic foods. You might think of lemons, you might think of certain type of candy, citrus things, so even orange juice, stuff like that. Those are going to be acidic foods. Pop. They change litmus paper from blue to red. So if we have these little paper strips, and you may have used those in the past, they'll change the paper to red. So red normally signifies an acid when we're talking about litmus paper. Acids normally react with metals, so they will break down metal. Their pH, so when we look at pH, that's talking about the pH scale. And I hope you talked about this at one point in your life. But at one point in your schooling. The pH scale, it goes from 0 to 14. 7 is the middle, that's neutral. Everything to the right-hand side, from 7 to 14, would be considered basic. And then everything from 0 to 7 would be considered acidic. So acidic things or acids, they tend to be less than 7 on the pH scale. It's just it's a way of us measuring the strength with numbers, I guess, of an acid. So we can use strips for that in our class, or we have different machines that can tell us what the pH is. They're corrosive. So corrosive means, if you look back to what we talked about in the safety unit, corrosive means it can eat through things. So it eats through, it would make your hands really dried out like bleach or something like that. But bleach is a bad example because that's actually a base. But something that is an acid that would, sort of dry out your hands. Acids, they neutralize bases. So if we had a base and we wanted to bring it, let's say I had a base and it was like in this range, and I wanted to bring it closer to this range, then I would add a acid to it. So if we add those two together, then they'll sort of cancel each other out and get closer to that neutral zone. So if we have a base and we want it to be more neutral, we add an acid. If we have an acid and we want it to be more neutral, we add a base. Okay? And that's something that, I don't know if you've ever heard, but if you get a jellyfish sting, jellyfish stings tend to be, I believe, acidic. So it puts an acid sort of in your skin, which makes you burn, and it has you have pain basically. So by putting a base on that, which we talk about as being one of the things would be pee, people can, I don't know if you've ever seen this or have heard of it, but people will pee on someone who had a jellyfish sting, and that sort of is that base, and that acid-base reaction will neutralize it so it'll stop stinging. And I mean, that's like a last resort. If you're at a place where you have a jellyfish sting, there's these sprays that you can use to neutralize it. But I mean, it's something that is an example of an acid-base reaction there to neutralize. And then our last thing here is conducting electricity. So yeah, acids conduct electricity as well as bases do too. So I should go to bases. Bases, they're bitter. They change red paper to blue. So we think of them as being blue. They normally feel slippery. So if you think of soaps and stuff like that, those are all bases. They are pH of more than 7. They're corrosive as well as acids are. They neutralize acids, so we add them to make them more neutral. And then they conduct electricity as well. Substances that are neither acids or bases are neutral. When an acid and a base of equal strength combine, they cancel each other out, a process known as neutralization. Neutral solutions have a pH of 7. Okay, so when we think about pH, it's right here. pH means potential hydrogen, and this is a measurement of how acidic or basic a solution is. The pH scale ranges from 0 to 14. Here's a good picture sort of what some of the things in our life would be on this scale. So hydrochloric acid is the most acidic acid we can have. That's at 0. When we look at things that we can actually eat, we've got lemons at 2, vinegar at between 2 and 3, apples are between 3 and 4, tomatoes are at 4, bananas 5. So there's lots of things in the acid area where we can actually consume those. There are a lot of foods. More to the neutral area would be water. Normally our water's not neutral, it's between 6 and 8, but should be in that range. Milk is a little bit more acidic, blood is a little bit more basic, and as we move towards on the basic side, we've got baking soda, soap, ammonia, drain cleaner, all these things that normally we don't necessarily eat. So what I'm trying to link here is the fact that a lot of things, it's not going to be as harmful for you to eat things that are acidic as it would basic. And that's all because of neutralization. Okay. In our stomachs, we have stomach acid. So if we add acids to it, it's going to keep our stomach acid working. But if we add bases to it, so we drink some drain cleaner, that's going to start to neutralize the acids in our stomach. And that's not good because then our stomach is not going to be able to break down the food that it needs to. And then that could be dangerous to you. So basically, really important that we don't eat things that are basic. We don't eat soap. We don't drink drain cleaner. Baking soda, we do have it in small doses in our food, but you're not going to take a spoonful of baking soda and eat it because that's really gross. So these little paper strips that I was talking about before, they're pH indicators. They're used to tell us whether there's an acid or a base in the solution. So blue paper, when it turns to red, that means it's come in contact with an acid. And when red paper turns to blue, that means it's come in contact with a base. Okay, so this is just showing you what those strips would look like. So it starts out as a red strip, and if we put that in a base, it should turn blue. It should turn blue where we put the base on it. If we have a blue paper and we put an acid on it, it should turn red where the acid has hit. Okay, and there's lots of different substances that exist that are pH indicators, which is really helpful to us to be able to easily find out sort of if something's an acid or a base. Solutions that lie near either end of the pH scale, so very acidic or very basic, can be extremely dangerous due to their corrosive properties. Corrosion is the wearing away of material by a chemical action, and often seen as rusting, oxidization, or acid rain. So something that's a huge problem for metal is rusting, and things get rusted due to basically acids. That corrosive nature of an acid or a base. And it says at the bottom here, corrosive effects of acids and bases are increased by warmer temperatures, humidity, and the presence of salt compounds. So I was actually talking about this with someone the other day because where I'm from on the East Coast, they use salt on the roads in the winter, so they don't actually do that here, mostly because, well, maybe they do at some places, but it's too cold for salt. Salt is only good to, like, I think, -15, maybe -20, and then it's not really, it doesn't work anymore for melting ice. So where I'm from on the East Coast, they use salt because it doesn't get as cold there, and lots of vehicles get really rusted. So the rusting of vehicles there is way worse than here. I don't see half as many rusty vehicles, and that's due to the fact that we don't use salt on the road. So that salt compound is going to increase the chance of something being rusted. So be thankful, I guess, about that, or when you guys do get a vehicle, that it's not going to rust out as fast as it does on the East Coast. Acid rain, we can't avoid that anywhere, but the rain that comes from the sky is in the vicinity of 5 to 5.5 probably on the pH scale, so it's pretty acidic, where we want it to be more neutral, so that can affect lots of things, like vehicles and stuff, but also it's going to affect plants. How do plants deal with acid, like acidic water? How do rivers and stuff like that? The animals that are drinking it, and then the animals that are living in that acidic water, can they adapt? So there's lots of problems that arise from acid rain. Here's some uses for acids and bases. So there's some different ones here. Hydrochloric acid is the first one. It's used for toilet bowl cleaner, cleaning masonry, so I guess that's bricks. It's in our stomach, so our gastric juices, metal cleaners, make sugar and glue. Okay, so we need hydrochloric acid to create those things. There's lots of different things here. I'm not going to read through them all, but if we go over to bases, sodium hydroxide, that's our strongest base. It's used in soaps, it's used in creating clothing, oven cleaners, sink and drain cleaners. So lots of different things lots of uses for most of these. But if we look in general, the bases tend to be a lot of detergents and cleaners. And I guess the acid side tends to be more of something that is like, I guess, a burning thing. But it's also things that are in food. So carbonic acid, that's in our soft drinks, like our pops, that sort of thing. So looking at the different uses for those, and we see them a lot in our life, whether you know it's an acid or a base or not. All right, so that is the end of the chemistry unit. I don't think I'm going to put any more quizzes or little check-ins for this unit. So just try and finish up the booklet that you need to for Tuesday. And if you have any questions, let me know. Have a